Okay, let's dive right in and deconstruct the digital brain. In this explainer, we're going to get under the hood and see how an artificial neural network actually works. We're going to break down how these systems go from being just a collection of really simple, almost dumb little parts into a powerful tool that can learn and make some seriously impressive predictions.
So here's the game plan. We're going to build our understanding from the ground up, starting with the single most important building block, the neuron. Then we'll see how to assemble them into a proper structure, figure out how we can make that structure learn, and finally, we'll watch it perform a real-world task.
All right, to get a handle on a whole network, you've got to start small, with its tiniest component, the artificial neuron. And this idea isn't some newfangled thing from the last decade. Its roots go all the way back to the 1940s, and it came directly from scientists trying to make a mathematical model of a real biological neuron in the human brain.
I mean, that journey from just a theoretical model on paper to a physical, working machine like the Mark-I perceptron, that was a huge leap. This was actual hardware designed specifically for image recognition, and it really laid the foundational groundwork for what we now call modern AI. So think of this thing, the perceptron, as just a tiny little decision maker. It's basically the digital version of a single brain cell, and it's the fundamental piece we use to build all the much bigger, much more complex systems. Now, what's really cool is how this simple little unit actually works. It gets a bunch of information, right, but it doesn't treat it all equally. It uses these things called weights to decide how important each piece of input is. Then it just adds up all that weighted evidence and uses something called an activation function, which was basically just a simple yes or no threshold to make a final call and spit out a single output. Okay, let's move on and see how this all scales up. A single perceptron is useful, sure, but it's pretty limited. The real power, the magic, really starts to happen when we connect them together into layers. And this slide really nails the huge leap in capability we're talking about. A single perceptron can pretty much just draw a single straight line to separate one group of data from another. But a multi-layer perceptron, an MLP, well, that can learn these incredibly complex, curvy, non-linear boundaries. That lets it model way more sophisticated relationships in the data. So the structure here is absolutely key. Information flows in just one direction, kind of like a river. It comes in at the input layer, it flows through one or more of these hidden layers where all the abstract patterns get processed and transformed, and then it finally results in a decision at the output layer. Now, this is maybe one of the most important points to get. Those nonlinear activation functions that are used in the hidden layers, they're the secret sauce. Without them, stacking all those layers would be totally pointless, mathematically speaking. The whole network would just collapse down into a simple linear model, and it would be completely unable to learn any complex patterns. And different jobs require different tools. For those hidden layers, the relay function is usually the go-to because it's fast and helps avoid a tricky problem called vanishing gradients. But for an output layer where you need a simple yes-no probability, sigmoid is perfect. And if you're trying to classify something into multiple categories, softmax is what you want. It gives you a nice, clean probability for every single possible outcome. So, we've got the structure, we've built the scaffolding, but a brand new network is just a random collection of connections. It doesn't know anything. So how do we get it from that state to an intelligent system that can actually make accurate predictions?
This is the absolute central question of training a network. The process isn't like programming where you write a bunch of rules. No, it's much more like teaching. We need to find a way to show the network its mistakes and then give it a method to correct itself.
This loop right here, this is the engine of learning. It's a constant, never-ending cycle. You make a guess, you measure how wrong that guess was, you figure out which direction would have made the guess better, and then you make a tiny, tiny adjustment to every single weight in the network to nudge it in that right direction.
The loss function is basically the network's guide. You can think of it like a report card. After every single prediction, it gets a numerical score. A high score means you made a big mistake, and the network's entire goal during training is to tweak all its internal knobs to get that loss score as low as it possibly can. This analogy is just perfect for understanding how the network gets better. It uses a core concept from calculus called gradient descent. It calculates the slope, or the gradient, of that loss function. And that slope tells the network exactly which way is downhill, the direction it needs to go to reduce its error the fastest. So if gradient descent tells the network where to go, backpropagation is the messenger that actually delivers the instructions. It takes that final error score from the report card and works its way backward through the entire network, telling every single connection exactly how much it was responsible for the mistake and exactly how it needs to change. Okay, enough with the theory. Let's make this concrete. We're going to see how all these concepts we've talked about, the perceptrons, the layers, the loss functions, backpropagation, how they all work together to solve a classic problem, recognizing handwritten numbers. Our starting point is a simple image. It's a 28 by 28 pixel image of a handwritten digit. Now, to feed this into our network, we have to flatten it out. We basically unroll that grid of pixels into one long single list of 784 numbers, where each number just represents the brightness of one pixel. And here is the exact blueprint for our little machine. Those 784 inputs get fed into a hidden layer with 64 neurons. That layer is going to learn to recognize basic features, like loops and lines and curves. That is then connected to an output layer that has 10 neurons, one for each possible digit from 0 to 9. And after running that training loop thousands and thousands of times, this is what you get. For an image of the digit 8, the network spits out a set of probabilities. And you can see the output neuron for the number 8 is firing with a really high value, like 92%, while all the others are super low. The network is confidently telling us its prediction. So when you just step back and look at the whole thing, from a single, simple little neuron to this complex learning machine, the entire process is really about this incredibly elegant feedback loop. It's about making thousands of tiny, guided adjustments over and over again until this coherent pattern recognizing ability just sort of emerges. And this leaves us with a really fascinating final thought, doesn't it? The network is incredibly good at recognizing patterns. It can see. But it's so important to remember that this is a simulation of intelligence, not real consciousness. And that really raises the question, where is the line between just being a sophisticated pattern matcher and having true understanding?